Okay, so I'm going to start teaching now. So we are in 4.1F. Thank you for being here, my four lovely students. And last day we started looking at predicting which side of an acid-base reaction is favored. What did I do with my gloves? And we had decided that if we have a reaction between F minus and HCN, that HCN had to be the acid and that F minus had to be the base. Could you close the door, please? It's a little noisy outside. Thank you. Okay. Just close the door. Just close the door. Close the door. It's noisy outside. Maybe that was you. Probably. Okay. So we're on 4.1F. I did have someone cry this morning. It's one of those units. It's okay. It's okay. If you were in Chem 11 Enriched, you would have cried the whole way through, because that course just made us everybody cry. Okay, just remember you're still here when many aren't. 4.1F. If you don't have 4.1F, it is here. Okay. So we have HCN, which is an acid, and F minus, which is a base, and we decided that the hydrogen had to move from the HCN to the HF, and so our products were CN minus and HF. And the reactants we decided were favored. Do we remember why? Probably not, I'm guessing. Do we remember why the reactants were favored? Yes. Yes. Was it helpful that you had to run around the room and chase after me? Yes. So I would actually recommend that at some point, maybe next class, I'll have you guys be stronger and weaker acids and bases with each other, okay? Just to kind of get that lived experience of being on that side of it. Okay, so the stronger acid is better at giving away hydrogen. And if it is better at giving away hydrogen, it spends more time in its non-hydrogen form. Yes? So it spends more time in its unprotonated form. And its unprotonated form is F minus. So we spend more time over here. Whoops. And that means our reactants are favored. And we can go through and we can write all this in. The Ka of HF was bigger than the Ka of HCN. You know, we looked those up last day, so we decided HF was the stronger acid. And then just writing this stuff out. A stronger acid is better at giving away its protons. Since the stronger acid HF gives away its protons in the reverse reaction, yes? Then the reverse reaction is favored, and if the reverse reaction is favored, that means that the reactants are favored. What does that mean in terms of our KEQ? Is KEQ going to be large, in other words, bigger than 1? Or is KEQ going to be small, in other words, less than 1? It's going to be less than 1, yeah, because if KEQ is products over reactants, our reactants are large, yes? And our products are small. Since the reactants are favored, the denominator will be large and the numerator will be small. And therefore, KEQ is going to equal a small number over a large or big number, which gives us overall a small number. And KEQ will be small. In other words, it will be less than 1. So a couple of things that we should notice here before we flip to the next page. So don't flip just yet. If HF is the stronger acid, what can you say about its conjugate base, F minus? Is it the stronger conjugate base or the weaker conjugate base? It is the weaker conjugate base, weaker. Because HF was really good at giving away protons, that means its conjugate base is not going to be very good at taking them, yes? So if you're a stronger acid, your conjugate base will be weaker. And that means that Cn minus is our stronger base. What do you notice about the two strong things? Stronger things. They're on the same side and they will always be on the same side, okay? So our two stronger things are on one side, our two weaker things are on the other side. So we can write that down here at the bottom, maybe with a star beside it because it's quite important. The two stronger species, stronger acid and the stronger base, will always be on the same side. That means that the two weaker things will also always be on the same side, and the side with the two weaker species is always favored. Okie dokie. So now let's try another one. And I'm really regretting choosing this horrible long formula for an acid, so I might go back and change it. But we're going to live with it today. we have H2C65H5O7 minus. It's dihydrogen citrate. It's one of the, because only 3, if you have H3, C6, H5O7, that's is it citric acid or ascorbic acid? I think it's vitamin C. Okay, so this is vitamin C. Only 3 of the hydrogens are detachable. The other ones are not detachable. Yeah? That's why we put the 3 at the beginning and the rest of them are in the middle where you cannot touch them. Okay, so what do we have here? And in our next species, we have HSO3 minus. What do you notice about both of those species that makes this a little complicated? They're both what? They're both amphiprotic. We have hydrogen and a negative. We have hydrogen and a negative. So both of them are amphiprotic. What does it mean to be amphiprotic? Able to do what? Act as an acid or as a base, either donate a proton or accept a proton. Now, if they're both amphiprotic, then the question becomes, who will act as the acid and who will act as the base? There's a little bit, but there's one reaction that happens more than the other. And how could I figure out which one is going to be acting as the acid and which one will be acting as the base? We can use our data table. Yes, we can. So let's go look at our data table. We'll bring that back in a minute. Oh, and I've written so much stuff here. No. Okay. What do we have? We need, that's H3, C6H5O7. We want H2, C6H5O7. Okay, so there's that one. And the second one we want is HSO3 minus. Oh, look, there it is right there. Who is better at being an acid? The bigger one, right? And that's because the strength of acids is higher as we get near the top, yes, and it's lower as we go further down. You can also check out their Ka values. This one is 10 to the negative 5, which is bigger than 10 to the negative 7. Okay, so it's better at dissociating. So let's go back here. So this is stronger acid than HSO3 minus. What happened? Oh, it wants me to focus. Great. So what does that mean? Who's going to donate to whom? H2C6 blah, 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 blah is going to donate. And so we can go down here and we can say guy is going to give a proton to that guy. And that will give us then, what are we left with? Well, we've taken away one hydrogen here. So we're left with one hydrogen, C6H5O7. And we lost a positive charge, so the charge will now be 2 minus, sorry. Because it was 1 minus and we lost a positive charge, so it became 2 minus. HSO3 has gained a hydrogen, so instead of just having one hydrogen, now we have 2. What is the charge going to be on H2SO3? Nothing, because it started as negative and it gained a positive. Okay. And let's just fill in some of that stuff above there. The Ka of H2C6 blah, blah, blah is bigger than, therefore, H2C6H5O7 minus is the stronger acid and will act as a proton donor. Which is favored in the reaction, the reactants or the products? What did we do last time we wanted to figure out who was favored? Yeah, we're going to have to, first of all, we're going to have to decide who are the acids and the bases. And so we decided already that this guy was giving up a proton, so it must be the acid in the reactants. And this one must be the base because it's accepting the proton. Who is the acid in the products? H2SO3, acid, acid. No, that's my brain going dead. That's just me writing down random things. That's like when I go drive somewhere and I end up at home because that's where autopilot took me. Yeah. And I'm like, oh, this is not where I want to be. All right, so now we have to compare the strength of our two acids here. So when you have two amphiprotic substances, you actually need to make two comparisons. Before you know who's going to act as the acid or base, you have to compare the two amphiprotic things. Once you know who's acting as the acid and who's acting as the base, then you need to compare the acid in the reactants with the acid in the products. The biggest mistake people will do is they'll still try to compare these two instead of comparing this with that one, okay? So just make sure you do that. So let's now go look at H2C65H blah, blah, blah. So now we are no longer comparing with this one, because that was, we decided was acting as a base. Now we're comparing with the acid on the other side, which is the H2SO3. And H2SO3 is the stronger acid. So if we go back, H2SO3 is stronger, which means that H2C6 blah, blah, blah is weaker. Tell your partner, who is the stronger base? And you don't need to look anything up, you just have to look at this equation. Yeah, this is our stronger base. Because remember, the two stronger things are always on the same side. Yep, so the products are stronger. And that means that my reactants are weaker. Which side is favored? We always favor the weaker side. And I kind of, it logically makes sense to me, but back when it didn't logically make sense to me, it was sort of like I would think it was almost a little bit religious, because it would be like, you know, except for the expression is the meek shall inherit the earth, but I would change it to the weak shall inherit the earth because they are favored, okay, which is a little bit goofy, but it helped me remember it anyway. But it should make sense that H2SO3 is really good at doing its job, and so it ends up as HSO3, and it's too weak to take its proton back, so it spends more time over in its base form. HC6 blah 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 is really good at grabbing onto a proton, and it doesn't let go very easily, so it's going to spend more time in its protonated form because it holds on to it quite tightly, okay? So that's where we're at. So we have H2SO3 is the stronger acid. Since H2SO3 is the stronger acid, that means that the reverse reaction is favored, and therefore the reactants are favored. If neither of those methods of thinking about it work for you, you can also think of it as like a pushing war, where one acid is pushing this way, yes? H2SO3 is pushing that way, and our H2C6H5O7 is pushing that way, but it's not as strong. So if we're pushing harder, because this one is stronger, if we're pushing harder to the reactants, then the reactants will be favored. So that's also another way that you can think about it to remember. Okay? All right. Will the KEQ of this acid-base equilibrium be large, greater than 1, or small, less than 1? Remember, we favored the reactants. It's going to be small. It's going to be less than 1, since the reactants are favored. Okay, consider the following reaction. What do we see about these two that makes this one of the more challenging type questions? They are both amphiprotic, yes? Now, when I did this with my morning block, they had a little more time because morning block is 15, 20 minutes longer than this block because of the, I don't know. For some reason, it's just longer. I don't really understand it, but anyway. So a lot of people, when they were predicting it on their own, they were just like, okay, there's my acid, there's my base. Can you do that? And just do it like, oh, the one on the left is the acid, the one on the right is the base. No, you can't. You have to go and check what? Check the data book. So we have HCO3 minus, and we have HPO4. It turns out HCO3 minus is actually the base. I'm going to change this question for next time, so I flip them around so it's not, you know, you can't accidentally get the right answer. We go back here. So this one is stronger, and this one is weaker. Therefore, this one's going to act as the acid, and this one's going to act as the base. And now that I've done that, I'm going to cross these out because I don't want to use that information anymore, right? Now that I've determined that that's the acid and the base, I don't want that because I'm going to make a different comparison later. So let's take our hydrogen and move it over. So we have CO3, CO3, 2 minus, plus H2, PO4, minus. And I hope it's pretty obvious that CO3, 2 minus has to be the base because it doesn't have a hydrogen. And H2PO4 has to be therefore the acid. If you needed to, you could look and say who's giving it to whom. Okay. What will we do now to predict who is favored? Compare the two acids. So we're going to take this acid here and compare it with this acid on the product side. So going to our data booklet, remember we're no longer concerned with the HPO4 because we decided that was acting as a base. Now we want H2PO4, and that's actually the stronger one. So let's go back here. So this is stronger, which means that the CO3 2 minus is the stronger base, and that means my two weaker things are over here, and whatever is weaker is favored. And I'm really, really sad that I gave you 3 examples in a row where the reactants were favored. I have to change it up for next year so that you get one where the products are favored, but yeah, that was not well done on my part. Anyway, so KEQ is less than 1. If you get stuck doing this on your own, because your homework is to do 4.1F, okay? So the worksheet attached to this. It's going to be, yeah, and then I've got like there's a few other little things like, you know, the 5 properties of acids and bases. What's an Arrhenius acid? What's an Arrhenius base? What's a Bronsted-Lowry acid? What's a Bronsted-Lowry base? I have some more I have got a vocab sheet for you and some extra practice questions that you can do on the weekend. But basically, if you can do this worksheet, you've got most of the marks on the quiz on Tuesday. Okay, so go home, try them out. If you get stuck, the list of steps are right here. Okay, and yeah, that's it. You can stand here and do it. Oh, thank you. As long as you put your pencil away. Hayden, you're staying here.